Hey, we are going to prove Darboux's theorem, which says that derivatives have the intermediate value property. So here's the statement of the theorem. If f is differentiable on an interval ab, and if alpha satisfies f prime of a less than alpha less than f prime of b, or f prime of a greater than alpha greater than f prime of b, then there exists a point c in the open interval from a to b where f prime of c equals alpha. So basically, derivative functions have the intermediate value property. We are going to start by defining a new function, g of x equals f of x minus alpha x on this interval, the closed interval from a to b. And this is going to simplify matters for us because we have to find a point where the derivative of this function is 0. Because you see, the derivative of g is g prime of c equals f prime of x minus alpha. And in terms of g, we can restate our hypothesis by saying that g prime of a is less than 0, less than g prime of b. And we must show that g prime of c is 0 for some c in the open interval from a to b. The way we are going to do this is basically by arguing that, well, you see, g prime of a is less than 0. So at the endpoint a, the function g must be decreasing, at least locally. And at b, the derivative is greater than 0, so g is increasing at b. So this means that at some point on this interval, the function must attain a minimum value. And we are going to argue that the minimum does not occur at the endpoints a and b. And from this we can conclude that the minimum occurs in the interior of the closed interval. So, and this just means that the derivative at the point is 0 by a theorem which we have proved at this point. So if we can show that g does not attain a minimum at the endpoints a and b, we may conclude that there exists a point c and the open interval from a to b such that g prime of c is 0, which is going to imply f prime of c is alpha. Okay, so our argument is by contradiction. So assume for contradiction that g of a is less than or equal to g of x or x in the closed interval from a to b. So we are going to assume that g attains a minimum value at a. So this is what this means. Then we may write g of x minus g of a is greater than or equal to 0. And assuming that x is not equal to a allows us to assert that g of x minus g of a divided by x minus a than or equal to 0 for all x in the same interval without including a. But if you take a look at this, if this is true for every x in this interval, then this implies that g prime of a is greater than 0, which contradicts our hypothesis that g prime of a is less than 0. We conclude that g does not attain a minimum value on the interval, closed interval from a to b, at the endpoint a. Now we basically just have to repeat the same argument for the other endpoint. So assume now that g of b is less than or equal to g of x for all x in the closed interval from a to b. So g of b is a minimum value of function g. And then similarly we may write g of x minus g of b is greater than or equal to 0. And for x in the same interval without including b, because we want to divide by x minus b on both sides of this inequality, and we can't do that if what we are dividing is 0. So g of x minus g of b divided by x minus b is less than or equal to 0. And the sign of the inequality flipped here because x minus b has to be a negative number, because it's in this interval and it has to be in this interval, so it's not equal to b. Therefore, it has to be less than b and greater than or equal to a, which implies g prime of b is less than 0. So this quotient being less than or equal to 0 for x in this interval implies that g prime of b is less than 0, and this again contradicts our hypothesis that g prime of b is greater than 0. Therefore, we conclude that there is a point C in the open interval from a to b where g of c is less than or equal to g of x for all x in the closed interval from a to b, and therefore g prime of c is 0, from which it follows that f prime of c equals alpha.